There you go. All right. So what we're going to do is I want to make sure that, again, if you clean up all your equipment, I'll be ready. I'll feel really good. We won't really start the second lab till tomorrow, but today you're going to learn about that, and you're going to learn about the idea, the background information on how this stuff works. And then tomorrow, I'll let you pick your groups again. I don't mind. I really would like you to kind of scramble it up a little bit, maybe pick somebody else in a different group, or and it will be doing that. And it will be tomorrow. I don't know if some of you will get to the spectrophotometer or not, but some of you will probably, you could get almost all of it done tomorrow, but sometime tomorrow or the next day, you'll probably have everything finished. And then it'd be a matter of probably when you get back next Tuesday, I'll probably let you have a day to write that up, and then I'll move on to something else. So I think that's what I'm gonna do. And again, I might have a little mini little quiz after it's all turned in and everybody in the group knows what's going on. And then, but those are little grades. Those aren't really big grades like that. Okay, is everybody all right? All right, so what we're going to do is, even before Christmas, you started this titration project, right? And you know what I would do is, if you could sit down and run this through your mind, say, well, I remember the first day. As a matter of fact, didn't you have a logbook? The first day, man, we had to get this solid sodium hydroxide, didn't we? And we had to turn it, and we had to be careful. As a matter of fact, when you put it with water, why didn't you go ahead and just fill it up to the top? Do you remember that? Why didn't you just fill it up to the line on the volumetric flask and say that's it? Anybody remember that? Do you remember how we actually couldn't do that? I said just put water in there and then we'll let it cool. Yes.
Because like the sodium hydroxide heats up, so like.
Does anybody know why that happens? Why is it when I put sodium hydroxide in water, why would I get heat? It is. Why is it exothermic? They are. And so these ionic bonds that used to hold Na and OH together, you're actually, water's tearing them apart. And so that enough of that bond energy is enough to heat up the solution, isn't it? And that's why you have to be careful, because then now you got warm water. Actually, warm water takes up a little more space than cool water, doesn't it? Or room temperature water. That's why you had to do that. So just kind of, if you could just kind of run through your mind what happened. Oh yeah, we made our solution. What's that called? What's that solution called? What's the name of that when you know the concentration of that because you made it?
Titrant.
What is it?
Titrant.
Okay, now that's a good word. That's a good word. It is going to become our titrant. But what do you call any solution that you know the concentration because you made it or you bought it? It's called a known or a standard solution. That's right. Isn't that right? Now, what was the goal of titration anyway? What was your goal? You made a standard solution. Why? Why would you want to make a standard solution? And anybody can answer. Yes.
I think because we didn't know the molarity of the acid, so we were trying to figure out how much of our acid or base that we knew about would cancel out.
So in any case, if somebody asked you to do any kind of titration, you said, I know what you want me to do. You want me to make a known solution, unless you give it to me, and I'm going to let that react with a solution I don't know the concentration with, and I'll do my stoichiometry, and I will figure out the concentration. See that? That's really the goal of almost all your titrations like that. Okay, so how did you know that you were neutralizing? How did you know the acid was neutralizing the base? I mean, how would you even know that? Because they both look like water, didn't they? How would you even know that? Yes?
Because of I forgot the name of it, the phenolphthalein, yeah.
What is it?
The
Phenolphthalein, right. And it just so happens that there are many acid-base indicators. Some of them will change between pH of 2 and 3, some between 3 and 4. This one happens to change close to 7. So that was the idea that phenolphthalein comes pretty close. So if you don't mind, I guess, would it be asking too much for you to give me the numbers? Or do you guys have your numbers? You turned yours in. You don't have the numbers, do you? It's in your packet.
For what?
What I was wondering before I started, I was going to ask you about what did you get for the molarity of the acid with trial 1? what was the molarity of trial 2, and what was the molarity with LabQuest? You don't have your numbers.
Our average manual was 80%.
Okay, wait a minute. Shoot, what's gonna do with that? The only person turned in. All right, what I'd like, instead of the average, if you give me the actual, what did you find for the molarity? Do you happen to know what your molarity was? And let's do group 1 and 2. All right, who wants to go first? Who actually had the numbers ready? What do you have?
For our first round, we got the molarity was 2.018.
018?
Yes.
Okay, next.
The second round, we got 2.021.
Okay, next. And what did you get for LabQuest?
Oh, we got 1.99.
All right, so these are what you call end points, because that was a visual, visually you thought that's when neutralization took place. And this is where electronically it says that's really where the ions were equal. See that? And I had to use electronics to figure that out. So this one did a pretty good job. Looks like you had pretty close to 2, right? 1.99 here. All right, can I have another group? Anybody have all 3 numbers? Yes.
We had 2.02, 2.01, and then 2.04.
Ooh, okay. All right, that looks good. How about another group? Anybody have 3 numbers ready? Yes.
We had 1.994, 1.997,
Ooh, man, look at that.
and then the LabQuest was 1.997.
Now, my own opinion is I didn't necessarily think that the phenolphthalein would be exactly the same. I just thought it would be close. That's very unusual. Those are really, really almost like identical. That's really unusual. Okay, yes.
We got 2.001 for our first one, then 2.02 for the second one, and then we got the same LabQuest as Christine.
Oh, okay, you were in the same group. Okay. All right, anybody, do you have one more group or not? Yes.
Had 2.01, 2.01, and then 1.99.
1 point what? 99? Okay. Now, what's interesting is, excuse me, I have a bottle back there of 12 molar hydrochloric acid, okay? And so I had to make an unknown. And it is dangerous. And as a matter of fact, just every time I take the cap off, there's always little fumes, and I'm constantly I took my mask off, I had to blow to kind of keep the fumes away. If I was your dad, he probably has a hood. He has a hood. Hey, let's go to the hood. Okay. But his dad probably has a hood at UNCG where they can turn it on and all the fumes are drawn up into like a filter and then something like that. But I didn't have that. So I have to use my own breath to just kind of keep it away, because otherwise it'll get it in my nose and so it's a little bit dangerous. Now, what's interesting is that bottle saves the school a lot of money. By buying a big bottle, I can make my own dilutions, and I can save the school a couple $100 every 3 years, something like that. So anyway, I don't mind doing that. But what's interesting is what I really tried to make, I tried to make this. I tried to make a 1.80 molar. Now, oh, sorry. But I noticed this happening last year. Last year we had a little trouble with the LabQuest. I thought that was something else. But the year before that, I noticed it. And I went back, and now I looked at the bottle, and it did this. Now, what does that mean? See, that means that you didn't pay that much money for this. Why would we want to give you a bottle that's exactly 12.00 molar? You get that? If I wanted a 12.00 molar, I'd pay a lot of money for that, because somebody would have to actually test it, and those are expensive. Standard solutions are expensive. So even though I tried to make, with my mathematics, I tried to make a 1.80 molar solution, it's obvious that this must not have been 12. In my calculations, I use the number 12, but I can tell by all my great scientists, thank you, with all my great chemists, I can tell. And if you were a real chemist, I would go back and figure out the average here, and then probably put on the bottle what the real molarity of that bottle is. So see that? Even though I used 12 and I thought I made a 1.8, it's obvious. I don't believe all of you, none of you got 1.8, did you? So I don't believe that. I don't believe this bottle was 12 molar, and I'll probably go back, do some calculations, and I might even write on that bottle next year what the real, it's a brand new bottle, what the real molarity is. Anyway, there's a lot of science that acts like that. If you don't mind that kind of stuff, you might stay in science when you go to school. If you don't mind that kind of stuff and you're measuring and who'd you check that? How do you know that was 12 molar, you know? Like that. So anyway, it's obvious to me that the molarity had to be somewhere close to 2. What do you think? And if it was anywhere close to 2, you were fantastic. You were just absolutely fantastic. Again, I did not expect all the groups to be that close to the same number. You did a great job. I thought some groups would get 2 and some get 1.8, 2.1. Whatever you did, it seemed like you were doing a great job. Even with the equivalence point, these are almost identical. These are very, very close. So anyway, you did a good job. I just want to finalize that for you there. And again, even though I tried to make a 1.8, it's obvious. It's obvious that it wasn't 1.8. There's no way all of you would have gotten 2 and then it'd be 1.8. It's just not happening. So, all right, you're ready to change gears a little bit. Okay. First of all, what we're going to do, this next lab has to do with light. And I didn't have to look this up, but before you came in here today, I asked, I said for Siri, how many times is light referenced in the Bible? And if you want to get into this, they say, well, what about this? God is light. How many times is God mentioned? That was like 3,000. And how many times is this? So I just said just light. I didn't use any of the other words that kind of also mean light. You get it? Just the word light. If you have the King James Version, it's mentioned 177 times in the Old Testament, 95 times in the New Testament. And this is the New American Standard. And the way they translate it, you still get 143 and 86. New International Version, the way they translate it, they still got around 140 and close to 100 here. And this is the New Revised Standard Version, whatever it is. Whatever. Anyway, so you can see, it's definitely over, it's close to 300 times, maybe 300, maybe 200 something. Now, why do I bring that up when we're in science class? I certainly didn't think that way when I was younger. As a matter of fact, I was an atheist until I was about 31 years old. And that's another story. But I wouldn't have thought that way. I would have said, if somebody told me that light was mentioned, I would have said, well, so what? So what? But the more I have been in my Christian walk since I was 31, and the more I think about this, I think light is very, very important in science. I know it. The more science I've learned, it seems that light is very, very important. And as a matter of fact, what was one of the first things in Genesis 1? What was it? And it was, wait, why is that important? What's that one of the first things you want to say about light? Well, anyway, even though light can have many references, maybe Jesus can be light, there's different things. There's something about light in science. There's something weird. Like, for example, if you're a pitcher and you can throw a 90-mile-an-hour fastball, and then I put you on a train and a flatbed, and we're going on a train. The train is going at 60 miles an hour, and you set up and throw your 90-mile-an-hour fastball, okay? Relative to the flatbed, you still threw a 90-mile-an-hour fastball. But how fast was that ball going relative to the ground? It actually was going 90 plus 60. It was actually traveling at 150 miles per hour relative to the ground. Okay, and that's the way things happen, you know. Now, so if you're in a car, and I wish I had never done this, but I have to admit, did I at least once throw something out of a car like a rock? I did. And perhaps I shouldn't have done that. You know, try to hit a sign. I probably shouldn't have done that. But, so I'm going down the road and somebody else is driving, and let's say they're going 40 miles an hour. And I just kind of tossed the rock out. Well, I thought I just tossed the rock out, but it hit it really hard. Why is that? It was going at least 40 plus 5, and it was going pretty fast, wasn't it? Why did I bring that up? For whatever reason. If you are in an airplane traveling 1,000 miles an hour, and then you turn the lights on, how fast is the light going? And the speed of light is 186,000 miles per second, which is about 300,000 kilometers per second. All right. So how fast is the light traveling if I turn the lights on a jet going 1,000 miles an hour? Yes? What is it?
I wasn't.
What is it?
Same speed.
It's the same. How is that? How is that? How can the speed of light still be the same when why don't we go 3,000 miles an hour and turn the lights on? What's the speed of light there? It's the same. I can't even explain it. I don't know enough. I don't know. We don't know. I don't know why. There's something about the speed of light that, as of right now, and as of the last so many years, is constant. The speed of light is constant, right? It's little c, and it's constant. So I know there's something strange about light. Einstein would have had, he had a little trouble with different parts. He didn't have much trouble. He didn't have much trouble. But there were still parts of physics that he still wondered about. He thought, no, that doesn't sound right. And a lot of Einstein's physics has been proven right. But he said you can't you can't travel faster than the speed of light. It's like a barrier. Now, I like Star Trek. So how does that happen, you know? Well, Star Trek, whoever wrote Star Trek, they had this way around it. You could have a warp field around you. So if you generate a warp field, it kind of like insulates you from that law. And so now, if you put a warp field around you, you can travel at 8 times the speed of light, and you don't have to worry about, you know, you didn't get older and they did. You're kind of immune to the whole thing. And that's how they get around it in Star Trek and Star Wars and stuff like that. So anyway, I'm not here to talk about science fiction or science reality, not that, but I just want to tell you that when people have been studying light for a while, it's still kind of confusing to us. But there's certain things that we're going to do on this lab. We're not going to do that. We're not going to measure the speed of light. What we want to do is use some of the qualities of light to discover things. And I want to tell you about a really, really big idea in science. Okay, real big fancy word, spectrophotometry. Some people will even say the word photometry, and so what do you think this part of it means? What is any kind of metry? What's that mean? What is it? Yeah, to measure. And what about photo? Light. And what about spectro? And so what it looks like, this fancy word called spectrophotometry, we're going to be using the spectrum of light, so many, many different kinds of light, to measure something. Got that? Now, you can buy a cheaper version. You can have these things called colorimeters. And colorimeters only produce one wavelength of light. And if you want to study with one wavelength of light, you can buy a pretty cheap colorimeter. Now, you guys, lucky, not news, I did spread this out. I spread that money over the years. We actually have 4 spectrophotometers. Would I like to have 6? Yes. But they're over $500 a piece. So you have this little box, and it's about $500 a piece, and it's a great science tool. And anyway, what we can do is this one will allow you to study things with the whole spectrum of light, okay? Not just one color, but any color you want. Got that? Okay, so let's go into this. What is it that you know about light? So let's draw a wave. Okay, so we know that light travels in waves. As a matter of fact, they call it, what does EM stand for? When you hear about EM,
Electromagnetic.
very good. What is it?
Electromagnetic.
Excellent, man. So electromagnetic energy has properties of electric fields and magnetic fields at the same time. Now, I'm not a physics major, but if you were to go back and read, there's a guy named James Clerk Maxwell. I know you don't believe this. I have a T-shirt. It has the 4 and they're very complicated equations, but he was one of the first people to try to explain what light was. But even Isaac Newton in 1700s, even he was trying to explain what light was. So we've had this discussion about what light is for a long time. And it's kind of interesting. We still are not great at explaining what light is. Well, let's go back to this now. So here's this thing that's really traveling. Even though I'm showing it like this, it's actually, there's a part of light going like this, and a part of light going like this. There's probably one going like this. See that? So we know it has the properties of electric field and magnetic field at the same time. Okay, we also know that like physical waves, this is not a physical wave though. I can't actually see it. If I go to the ocean, I can see that wave. If I tie a rope onto that doorknob and I go like this, can I see that wave? I can see that. That's called a physical wave. My voice is causing the air to go compress, relax, compress, see that? And it's causing a certain frequency of sound to hit your eardrum. And it's going, and your brain says, I understand what he's saying. And so those are all what they call physical waves. You got it? This is not. This is an electromagnetic wave, and physical waves need material to move through. Ocean waves, does everybody understand about that? I did this when you were young, like 10th grade. When you see a wave out there and you're standing and your ankles are covered by the water at the beach, it's like, yeah, summer, beach. Okay. But let's say you're standing in ankle deep water. Here's a wave out there and you watch it and it hits your ankle. You see that? There's no way, as a human, you probably thought anything different than that water out there, it came all the way to my ankles and splashed up. No, it didn't. If you could put a marker die on that water and actually mark the water, you'd see that water go up and down, up and down. Next wave, up and down. And there's a bird. There's a bird out sitting there. What happened to the bird? Up and down. Well, if the water actually moved, then why didn't the bird come in with it? So what is it that's traveling through that water? Energy. And that same energy, when it gets close to your ankles, it throws the same water up at your shins. Well, again, those are physical waves, but this is actually something different because physical waves need to travel through something. Like if I put my ear down here and I go, okay, the vibrations are actually traveling through that table. See it? And that's okay. But this can travel through nothing. It can travel through vacuums. It can travel from the sun here through nothing. So we have to be careful. Does it have the same properties as some physical waves? Yeah. But is it a physical wave? No. So we have to be careful with that. But because physical waves have what we call wavelengths, we still think that light also has wavelengths. And what is a wavelength? Oh, go ahead. I'm sorry.
If they're not physical waves, then what are they?
Okay. That's a great question. That's a great question. I don't think I have a good answer for you. I will say that as if you were to study light even more, you'll talk about the age-long battle: is light a real wave, or is it made of particles? Is it just energy traveling in waves, or is it particles? And even Newton had that argument. He said, here's some experiments showing that it's clearly a particle. Here's some experiments showing it can't be a particle. It has to be an energy wave. So we had this thing called the dual nature of light for a long time. And we still believe it has a dual nature. So it has the nature of being a wave and it has the nature of being a particle. Today, you would say that those particles are called photons. Okay, so photons are little bundles of energy that seem to travel and have a wave-like characteristic to them. Well, I want to actually get to spectrophotometry, but I don't want to get too much into the physics of this, but this little lambda, Greek letter lambda, whenever you see it, it means wavelength. So lambda, and if you go to college, you get in a sorority, or I don't know if that's up to you. It's up to you what you meant. But you've probably seen these Greek letters on sororities and fraternities, right? But anyway, lambda is what they use for wavelength. And then if I draw another set of waves, I notice that this one, its wavelength is shorter. So this is a longer wavelength, and this is a shorter wavelength. Now, what's interesting? It's interesting is they use this symbol here, as a matter of fact, for frequency. The speed of light is equal to the wavelength times its frequency. Now, I don't know if you remember from physics class, but if this is a constant, then how are these two related? What's the mathematical relationship between wavelength and frequency if the speed is constant? What do you remember? As a matter of fact, and they do it proportionally. So if the wavelength were to get 10 times greater, what would happen to the frequency? If this got 10 times greater, what would happen to frequency? It would get 10 times smaller. Now, I want you to think about this. Both of these are traveling at the speed of light. What is frequency? Frequency would be, but how often one of those waves hit me? You get that? And so if I had these really long wavelengths, how often would a new wavelength hit me? You say, well, not as often. So if the bigger the wavelength, the lower the frequency, right? Everybody got that? And what about small wavelengths? The smaller the wavelength, the higher the frequency. Okay, now, it just so happens that frequency and energy are directly proportional. Directly. So if you have low frequency, you also have lower what? Energy. And if you have a higher frequency, you have higher energy. Now, we'll talk about this again. Besides spectrophotometry, we'll talk about it again near the end of the year when we do a quantum mechanics. We'll get back to this a little bit. But does everybody have the basics of light? Does everybody kind of like the basics? Okay, so what do you know about the EM spectrum? What do you know about the EM spectrum? Like, what about that? What do you know about the EM spectrum?
There's some colors we can't see because they're too slow.
That's right.
Frequencies are too low or too high.
That's right. Now let me minimize this. Let's see. okay, so here's an EM spectrum, and EM is electromagnetic waves. That's light. When everybody says electromagnetic energy, you say, "Oh, you mean light?" Oh, yeah, that's what I mean. Okay. So here's what happens. We have wavelengths, and oh, dang, that one doesn't show the numbers. That doesn't show the numbers. Let's go down.
Yeah, that's the nanometers.
It does?
Uh,
Oh, there they are.
Colors.
Ah, wait.
Like if you.
Oh, it's a video.
Yeah.
Okay. Okay, that's fine.
Grammarly does more than catch errors. With Grammarly, you can find really good. No.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum.
Oh, back. Okay, so how long are some of the longest wavelengths? And even though this book says 10 to the third, I've seen 10 to the fourth. But do you understand what 10 to the third meters is? That's like, here's a meter stick, right? Now go 1,000 meter sticks. And that means that wave starts up here, it goes down, and when's it come back up? A kilometer away. That's a huge wavelength, isn't it?
What would you use that for? Like what kind of?
Okay, now, when we found out there were different wavelengths, some people figured out what to do with them. What we end up doing with the long wavelengths is we send radio and TV signals. Whales have some pretty long wavelengths. They actually communicate a couple miles away to another whale. And anyway, so let's go ahead, and I just want you to look at, these are some big wavelengths. These are radio waves, TV waves. That's the way they send signals. Now, in your generation, I have to be careful because you guys have cable. And so the way they do it now, they send it through fiber optics maybe, but still at the speed of light. But the way they used to do it is actually send it out in the air, and it would travel a long distance. And let's go ahead and start this a little bit more.
With the longest wavelengths and lowest frequencies in the spectrum, a single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy
Which are
due
still
to
kinda
shorter
big.
wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy.
These are the ones
in
that can hurt
comparison
you.
to the football field
You
size
understand that? The real
wavelengths of
short
radio
wavelengths,
waves.
that's
Gamma
what
ray
can hurt you.
wavelengths are as small as atom nuclei.
For thousands of how-to and advice videos on any...
Thank you very much. Okay. Now, let's talk about this a little bit. All right. What I'd like you to remember is that if we were to go this way from short to long, short wavelengths, what was that number for gamma rays? Anybody remember the number? 10 to the what? Negative what? Negative 12, okay. And I've seen some books go down a little bit lower than that, but let's say this. 10 to the minus 12th meters, and up here was, and again, some books I've seen are 10 to the 4th meter. So we know that light can travel in many different wavelengths. And that's a great question EJ asked. What can you do with that? Well, what I do with a microwave is different than I do with a radio wave, isn't it? Okay, now, what I'm really interested in this lab is, yeah, go ahead. Oh yeah, sorry. What I'm interested in this lab is this zone here. Now, the smaller, if you go right outside the zone of visible light, you get UV light. Now, UV is ultraviolet, is that right? Now, you can't actually see ultraviolet, but it has a wavelength that's a little bit smaller than visible light. What was the smallest number? Here's Roy G. Biv backwards. Roy G. Biv. There you go. Here's Roy G. Biv backwards. And so this visible light is what you can see. Everything right now, everything that's coming into my eye, my brain's interpreting if it is visible light. There's some ultraviolet given off, but I don't see it. There's infrared, but a lot of you giving off infrared. You're hot, aren't you? I don't see that either. So here on both sides, I have either ultraviolet or infrared. But what were the wavelengths that you're going to be dealing with in the lab that we do? We're going to stay. You can get a spectrophotometer that goes into ultraviolet. It just costs a lot of money. But we can go here. Does anybody know this number? This is the one I want you to remember. 400 to 700. What is that? What units would that be? Is this in meters? Nanometers. All right, so what I'm going to do is I want you to imagine that you have the ability to use different wavelengths of light. Yes, I'm sorry.
Can you speed your paper up a little?
Yeah. What if I told you you have a machine that when you plug it in, it has the ability to send all of these lights, every one of those wavelengths, toward your sample. Okay? So it's going to go toward your sample. Now, sorry. So here's what's going to happen. You're going to have a sample, and I'm going to let light come in here. Now, I want you to use your imagination. Tell me what can happen to that light. What's one thing that can happen to that light if it goes into my sample? And that'd be my unknown or known. What is it? Okay, it might reflect it. What else? One more? Okay, it might go right through it. So it might be reflected. It might be, number 2, transmitted. And what else?
Like stopped, like blocked.
Why would it stop? Oh, blocked. Okay, now, it's true if I were to put something opaque, if I put something opaque there, do anybody know why light doesn't go through a brick? How about a thin piece of brick? How about a thinner piece of brick? What's the word here? Okay, so light can either be reflected, it can be transmitted, or it can be absorbed. Okay, is everybody with me? Okay, now I want you to imagine now that you have a choice of what wavelength of light you want to put in here. And then let's say we have a chemical in here. And you said, hey, chemical, I want to know how concentrated are you? And you hold the test tube up to your ear, but it never talks to you. And so it doesn't ever tell me the concentration. So what are you going to do? You have to find it out, don't you? If you're not going to tell me, I got to find out. So when I have a chemical in there, let's pretend it's yellow, or let's green. Let's pretend it's green. Let's pretend that's green. As a matter of fact, if it's not green, if it's clear, I might be able to put something in there to make it green. See that? And I might have something in there that only makes that chemical green. Ah, you thought I couldn't see you. Now I can see you. Now let's pretend that we have test tubes, and here's a test tube, and here's a test tube, and here's a test tube. And this one has a lot of that chemical in there, a lot. And this one has less, and this has even less. See that? I want to know how concentrated you are. Oh yeah? I'm not going to tell you. You got to find out yourself. Okay. The first thing I want to do is I need to find out what wavelength of light do you absorb? What wavelength of light do you absorb? And that's what you're going to be able to do in this lab. You're going to first find out what wavelength of light does that chemical absorb really, really well. Well, let's pretend. If it's, by the way, it's green. If it goes from 400 to 700, it would not be somewhere in the 5 to 600. That's where green is, isn't it? So maybe I'm going to throw some 400 nanometer light at you. And here it comes. Okay, now, you will absorb red light. Why do you even look green? I don't absorb green. I let green go right on through it. I ignore it. So there are some wavelengths of light that this chemical ignores. And other chemicals, other wavelengths, it says, I like that one. My structure says, I'll absorb that. I'll absorb that. I'll even absorb that. I'm not absorbing green. Okay, so now, what's on here? What do you think would happen then if I run this light through here, here, and here? What's going to happen? Who's going to absorb the most amount of light? The one that has the most chemical, right? And what about this guy? You see that? Now, I want you to think about this. What if you were to make a series of standard solutions? You made one standard solution, and then you made serial dilutions. You made dilutions of your solution. Would you know those concentrations? You made it. So you would make a standard curve, and you could say concentration versus, I don't know, if you want to make molarity, we can do that, okay? And so, I'm sorry, absorption. So what if you had the one that was not very concentrated? How much would it absorb? Like almost nothing, right? Is that right? What about the second test tube? So let's say this is test tube, this guy here. How about the next test tube? It's going to absorb more, and it's going to absorb more. But you see what I'm doing is I'm making what they call a standard curve, also known as a calibration curve. So you make a standard, or sometimes called a calibration curve. Now, a lot of you don't like me saying the word curve because it's a straight line, but it's still called a curve, whether it's curves or not. Now, this is my known. Now, I hand you another test tube, and I say, I'm not going to tell you how much I put in there. You said, that's okay. That's okay. I'm going to find out. What if I put my unknown in there? I'm almost done. Ready? Watch. What if I put my unknown in there, and it gives me an absorbance reading of that number there? Boink. Boink. I found you. Can I find the unknown by comparing it to results from known? All right, tomorrow. Tomorrow you'll probably spend most of the time making the standard solutions and learning how the spectrophotometry works, okay? Yes.
I couldn't get ours to staple.
What now?
I
Oh.
couldn't get our titration project to staple.
Oh, you can't get it to staple. Okay. See if that works.
Okay, thank you.
Thank you.
All right, thank you very much. Take it. Ooh, look at that. Ah, look at that. That's beautiful. Bye bye. Oh. That probably took a little longer than I wanted to, but I know we're switching over. Everything's got to be different. So when you start the lab and they'll start talking about wavelengths, absorbance, I want you to know a little bit about what's going on. Yep. This is used all over in science, like all over the place. Spectrophotometry. I almost for certain, if you go to college and take a chemistry lab, one of your labs will be spectrophotometry. One of them will be titration, probably.
All right, we'll give both the best of both worlds.
A lot of colleges still have not gotten to the electronic pH. Some are still doing just phenolphthalein method.
Really?
So I feel pretty good that we actually do some things that they don't do, but there's no way I can keep up with them. I can't, but.
Yeah, well, we know what to do both now, so if we need to do electronic or phenolphthalein.
That's right. That's right. And when you get, as long as you have a taste of spectrophotometry, it doesn't matter whether they have LabQuest spectrophotometer or another kind, you'll understand the idea behind it.
Thanks, Mr. Feeney.
All right, bye. Okay, hey. All right. So, I'm really, if this was a pushover test, and everybody got an A or B, then, I'm gonna, let me show you the stats. Now, your class didn't do as well as the other class, but I'm not interested in that. I'm interested in how you did, okay? And you got, you were right about, I gotta start this, I gotta put the initial count, okay? But, the lowest A was 126, and I believe you got, I think that might be you. I don't think that's you, I think this is you, but you're still only 6 points away from A, which is really good. And it would be in the second, maybe the second highest. I'm gonna double check. You could have been the second highest in your class. That makes you feel good. All right. So really, I got a second high. You beat almost everybody except one person. Okay, one person beat you. Now, unfortunately, nobody in your class got an A. They got a B plus. And yours is getting close, but you still had the second highest. And then I want you to look at it here. I'll show you the answer key here. And if you have time, you don't have to do it now. But if you want to come back and say, I'd like to look at the ones I missed, because the good news is, even though you missed more than you thought, let me double check that. You did really well in this part. This part here, you got bonus points, anything.
Attention DR students, call school has now begun. If your name is on the list, you may be dismissed. Also, if you are missing your phone, please come and get it in the DR office. Thank you.
And so, instead of having a, yeah, there it is. And then you got 3 bonus points here. And so that helped a great deal. That means you had -20, 140 -20. So if you have time to look at some of these, and you say, well, I could have got an A. If 6 points away means 2 questions plus a piece. So a little bit more than 2 questions would have given an A. 3 questions for sure. So if you have time, if you want to look at it, you can. I'll link right there. If you want to look at it, you can. If you want to find your actual questions, you can do that. Or you just go, say, I'm really happy. And
I'm sorry. I'll wait, you're finished.
no, I'm just telling her, there are some tests that you haven't done so well. Okay, but this test, she worked, I don't know what it was, or what, I don't know what clicked or whatever. But, oh, see, you find that right person.
That does make a huge difference. Yeah, just,
Maybe you can do that.
yeah. I'm telling you, that's, my daughter is super, I know this sounds obnoxious, she's super successful at college. It's kind of ridiculous, because she has a different study group for every, she was freaking out last semester because they all got sent home, which meant
No study groups.
no study groups. All of my grades are gonna be in the toilet. So yeah, so I'm glad you found something that works for you for your toughest classes. Keep doing it.
She even showed up at 7:30 in the morning, and did that last minute review, and did that help at all?
Yeah, here, I'm licking my finger. Cause you'll find Hicks, Michael Hicks.
That's it.
I had to look it up in the yearbook. Okay.
Okay, but anyway, it's up to you. You say, I'm just glad, I'll look at it later. I will eventually let everybody look at it, or you can sit here and do it now.
I'll just look at it later.
Okay, all right, there you go. Well, congratulations. Like I said, if you somehow get on that and it works, then we'll get back into testing later. Right now we're doing lab, but we'll eventually get back into testing.
Thank you.
All right, bye. Good job. Yeah,